So here's another way of looking at this schematic diagram of a power plant. Okay, we call this transfer of energy thermodynamics. Okay, it's how we keep track of and model the movement of energy from one form to another. And as it turns out, the first law of thermodynamics is actually the law of energy conservation, and that is that energy is neither created nor destroyed in the universe. And so the important thing to note here, a lot of times when people hear that energy is neither created nor destroyed, that energy is conserved, they think, well, then we don't have an energy crisis because we can always transform it, back into, a useful form of energy. But the problem is that every time we transfer energy from one type to another, in the form of work, we do what we say, quote unquote, lose a little bit of energy in the form of heat, and it's still there. It's just not useful energy. It's just random vibrational energy that eventually is lost to the outer universe outside the Earth, to the rest of outer space in the form of heat. So if you start off with all of this potential energy that we have in the fuel molecules, that we have in what they call the fuel reserves down underground, if you start with that potential energy that took years and years to accumulate all of that potential energy, and then you just very quickly burn it in the burner, that potential energy is then converted to kinetic energy. The kinetic energy is the movement of the water molecules as they move from the liquid to the gas. Then the gas is directed through a pipe. It needs to be directed through a pipe so that it can flip the paddles of a turbine, and they say that it's converted to mechanical energy, but really that's just another form of kinetic energy. In the generator, you set up this electric potential, which is a potential energy difference for the electric energy, and then it's converted to another form of kinetic energy, the current, as it moves through the wires. So a lot of times when we talk about energy transfer, it gets a little bit confusing because we say there's only two types, kinetic and potential, and then all these other types show up, mechanical, electrical, and whatnot, but they're just variations on either potential or kinetic. And the other thing that's important to keep in mind is how you view your system. When we think of the potential energy of the fuel molecules, we're thinking on a microscopic scale, literally the relationship of one atom next to the other atom. It's electrostatic potential energy in these chemical bonds. And then when the potential energy is converted to kinetic energy, again, we're thinking of, as the energy is transferred to heat energy, really what's happening is the molecules are moving faster and faster, which we perceive as more thermal energy or a hotter situation, because it is. So we have to go back and forth between kinetic energy and potential energy on a macroscopic scale versus a microscopic scale. But the microscopic kinetic energy of the molecules is what does the work to drive the turbine. So it is a conversion of microscopic kinetic energy to really macroscopic kinetic energy, but it's still all kinetic energy. It's energy of movement. And that is done by an energy transfer called work. Okay, and then all the way out to the energy transfer. So every time we transfer energy, we are either giving off heat, or we are giving off, or we are doing work, one or the other. That's the transfer part. Okay. Let's see. So let's be specific about defining heat and work. So there's two different types of energy, kinetic and potential, but they move, or energy is transferred in the form of heat or work. And so heat, a lot of times we abbreviate heat with a little lowercase q. That involves the transfer of energy between two objects due to a temperature difference. It's unorganized energy transfer, and it's due to the vibrations of the molecules. And we saw that last time when we recognized that infrared radiation increases the vibrations, and we know that that is a way of heat transfer through infrared radiation. And then heat is given off by a chemical change, and that change is said to be exothermic. So anytime we have a chemical change and heat is given off, we call that chemical change exothermic. And then the opposite, if heat is taken up upon a chemical change, that change is said to be endothermic. So we have directional changes, whether heat is given off or taken up across a chemical change. And then, okay, so that's one way that energy is transferred, is in the form of heat. And the other way is in the form of work, and that's just lowercase w. And work, of course, is defined as a force acting over a distance. And this type of energy transfer is organized and directional. Okay, so whereas heat is unorganized and is just vibrational, the work is organized and directional. So we can have heat, for example, a transfer of heat energy from the burner to the water by conduction, heat conduction, and then the water molecules pick up that energy in the form of heat, and they can then do work when they are, when you put them and when you force them to go through a certain direction, for example, up a pipe. Okay, if you don't have any kind of machinery around your, say you're boiling water and you're just boiling it on the stove and you're not capturing the steam in any way, then you're not going to get any work out of that system. You're just going to be that energy is just going to be transferred into heat. It's just going to be dissipated throughout the surroundings. But if you're thoughtful about how you manufacture your tools, then you can catch that heat energy in the form of steam and direct it through a pipe. And because you've added direction and you've organized it, you can get it to do work for you. For example, turning the paddles of a turbine, which can then generate electricity.